Okay, this is the first lecture for chapter 19, nuclear chemistry. Now, nuclear chemistry is an interesting topic because we start to break some of those rules that we've always had since you've been learning chemistry. Right? We were always taught that when we balance our chemical equations, that our elements, whatever was on the left, have to show up on the right. And now that is changing a little bit as we get into nuclear chemistry, which is starting to break or bend some of those rules. So, nuclear chemistry kind of came from the discovery of radiation, right? And so radiation was found by Antoine Henry Becquerel, right? And what they were doing was they were designing an experiment to determine if phosphorescent minerals also gave off these X-rays. So phosphorescence is the long-lived emission of light by atoms or molecules that absorb after they kind of that is observed after they absorb some light. So X-rays are detected by their ability to penetrate matter and kind of expose a photographic plate. So what we were trying to do is we were exposing materials that to light. We were seeing if they were giving off light afterwards. And then we were going to look at that and we're going to see if the light that they were releasing had the ability to penetrate a plate and be detected on the other side. And so Becquerel discovered that certain minerals were constantly producing energy rays that could penetrate that matter. And so they determined that all minerals that produce these X-rays contain uranium. And so the rays were produced even though the mineral wasn't being exposed to energy. So unlike phosphorescence, they didn't have to be exposed to more light in order for this to work. These minerals were constantly releasing these rays. So he called them uranic rays because he associated them with uranium. And they were like X-rays, but they weren't related to phosphorescence. They didn't have to be exposed to light before that they occurred. So this was the beginning of radiation. And so Marie Curie is probably one of the more famous scientists that started to work with it. She determined the rays were emitted from specific elements. She discovered that new elements could be detected by, she also discovered new elements by detecting their rays. So she found something called radium, which we used to use in our, which is named for its like green phosphorescence, which was kind of used in glow-in-the-dark or watch faces, and polonium, which she named after her home in Poland. And because they were no longer just uranium that were releasing these rays, then she changed the name from being just uranium rays to being radioactivity. So she kind of coined that phrase. But at this time, they didn't quite know all of the dangers about radiation. They didn't know about those other risks that could be caused from that exposure. And so it was one of the things that ended up costing her life later on, despite her great advancement that she did for us in moving that forward. And the reason why is that radiation, they can ionize matter. So that means that they can change uncharged matter to become charged. This is the basis of the Geiger counter and the electroscope, which we use to measure radiation. Now, the reason why radioactive rays can ionize matter is that they have a high energy. Now, that high energy means that they can sometimes penetrate matter, and they can also cause phosphorescent chemicals to glow. Now, this concept of radioactive chemistry or nuclear chemistry actually has its foundation back in alchemy, which is the beginning of chemistry in some ways. Now, alchemy was always obsessed with this idea of transforming one element from one kind to another. And at that time, they had never been able to succeed in doing it because what they didn't know is that in order to do this change, to change one element to another, it requires a large amount of energy, a huge amount. And so this isn't possible with normal chemical reactions, which is why Dalton's atomic theory held true for so long. But now, as we are getting into nuclear chemistry, we're going to start to see these chemical reactions that could have enough energy to start to change some of those processes. So in order for us to go from one element to another, this requires a change in the number of protons in an atom in order to form that new element. Now, when atoms are formed, there's something called the mass defect that is produced. And this defect is because there's a difference between the sum of the mass due to the protons, neutrons, and electrons of the atom and the actual mass. So if we were to measure up all of the atoms, the protons, neutrons, and electrons for, let's say, carbon-12 right here, they all add up to 12.0993 grams. But we know that the mass of 1 mole of them is just 12 grams. And so there's a change there. And that change is because when that atom was formed, some of that mass was converted into energy. And that is called the binding energy. So this energy corresponds to the missing mass that we see, and it's used in the formation of the atom. So it's a huge amount of energy. You can kind of see here, this binding energy is on the scale of 10 to the 8 kilojoules per mole. When you think about our normal typical reactions, we are maybe in the 200 kilojoules per mole. Sometimes we might get up to the 1,000 kilojoules per mole. Now you're talking about oh, 100 million kilojoules per mole. There we go. So it's a much larger difference. Now, not all elements have the same binding energy. And you can kind of see that here. Our lighter elements start off increasing their binding energy quite quickly. That's what this growth is here. But it kind of peaks in our iron range. After iron, when we start to divide that binding energy based on how many nucleons, so nucleons are your protons and neutrons, we start to see a slight decrease in that. And so if you wanted to kind of think about it, your nuclear binding energy divided by your nucleon is a little bit related to your nuclear stability. We're kind of increasing in our stability as we move all the way up to our iron. And then after that iron, we kind of slowly fall down as we move higher than that. So the highest nuclear binding energies are between 40, or for atomic number 40 to 100, kind of in that range right around with our iron. That means that the net attractive forces between the protons and nucleons and neutrons are strongest for these elements. And so their nucleus is the most stable. Now, when we're engaged in this chemistry, breaking apart an atom into components and rebuilding them as different elements requires billions of kilojoules per mole of energy, which is what we just saw. So when we're looking at this nuclear binding energy, what this is telling us is that if we want to go from hydrogen to helium, it's not a small amount of energy that's in there. If we need to break apart those protons and add them to the next nucleus, we need billions of kilojoules to make that happen. Now, there's no way a chemical reaction can generally do that. So if you look at it, it's normally like we have our nucleus, our protons and our neutrons, and all of what we're doing with our exothermic reactions isn't enough to change their elemental makeup. The reason for this massive change in their energy is that the nucleus is held together by something called the strong force. And these are really short range attractions between the proton-proton and the proton-neutrons inside the nucleus. And so this short-range attraction is what's going to allow the protons or the nucleus to hold together despite those proton-proton repulsions. The neutrons in some way kind of help reduce the repulsions between the protons. And so as we get higher in our size, then we need more of those neutrons to help balance out those attractions. So radioactive atoms, they get their name because they undergo a spontaneous change in their nuclei. So they're going to spontaneously change by themselves in order to become a more stable state. Now, in our light elements, less than 20 for our atomic number, our neutron to proton ratio is roughly about 1 to 1. As we start to get higher than that, as the atomic number increases, we start to see more and more neutrons get added into the mix, so that N to P ratio, that neutron to proton ratio, increases. And so this is what we call the band of stability. Now the band of stability is for our isotopes of elements, which are mostly stable. So they can have some decay that's in there, but they are going to be our mostly stable elements. So if we have a nucleus that kind of fits inside that band of stability, we're going to have them have a half-life or so like a half-life stability where we can start to measure them. If they're outside that plot of stability or that band of stability, then they will start to decay so quickly that we won't be able to see them. So the belt of stability in general is 1 to 1 when we're very small, and then it's greater than that as we get larger. So that's what the band of stability is talking about. If we're outside that belt, we can definitely be considered radioactive isotopes. And then inside the belt, we're normally considered non-radioactive ones, or at least we have a long half-life because it's something that we can measure. So stable is kind of defined as non-radioactive isotopes with measurable half-lives. Now this nuclear stability, in the same way we have electron stability for our noble gases, when we have 2, 10, 18, 36, 54, 86, there's something similar with our neutrons and our proton count. So certain numbers, 2, 8, 20, 50, 82, 126, are elements that have an exceptionally stable nucleus. Now, you don't have to memorize those numbers. It's just something that you, it's kind of nice to know as you move forward. But there's these magic numbers between the right ratios of neutrons and protons, which make these elements extra stable. Element 50, or so a nucleus with neutrons or protons at 50 is extremely stable compared to one with 51. It's also even numbers of both protons and neutrons seem to be more stable than odd numbers of neutrons and protons. And then the last part is all isotopes with atomic numbers higher than 83 are radioactive. So when we look at this, when we're kind of trying to think of the stability, when both odd protons and odd neutrons, there's only 4 stable isotopes with that. An odd and even mix, they account for 103. And 164 of our stable isotopes have both an even number of protons and an even number of neutrons. And so there's still a lot of theory and work being done about why that is, but we just wanted to introduce that idea that the nuclei are not all as stable as they have been said to be. There is a change within those nuclei depending on our ratio of our protons to our neutrons, depending on do we have the even numbers of both, and even about what total number we have, which are extra stable. So for these processes, when we're not stable, those nuclei can go through radioactive decay. And so radioactivity is the release of these tiny high energy particles or gamma rays from an atom. So particles get ejected from the nucleus, and they get ejected with a lot of energy. Now there's different types of radioactive decay. There's alpha rays, there's beta rays, there's gamma rays. And there's also some called positrons, which is like a positively charged electron. So we're going to look through some of these, and we'll look at what that kind of radiation looks like and how we can discuss it. And then we'll talk about some of those processes that our radioactive materials can go through, such as how they can go through something called electron capture, where a low energy electron is pulled into the nucleus. So we're going to be looking at different types of decay in our next section. Now, to help us with this, we're going to practice writing our nuclear equations. So in order for us to write our nuclear equations, we need to use the full symbols for our elements. So we're going to start to write the mass number as well as the atomic number. So this is the full symbol for a neutron and a proton. So this is a neutron, and you can see that it has a mass number of 1, and then it has 0 for its atomic number because it doesn't have any protons there. A proton, on the other hand, has a mass number of 1, and it has an atomic number of 1 because it has 1 proton. And so take a moment to think about this. Why do they both have the same number? Why is the atomic number for a neutron 0? Why is the atomic number for a proton 1? And so they both have a mass of 1 AMU. The neutron doesn't contain a proton, which is why it has an atomic number of 0. And the atomic number is 1 for a proton because it has 1 proton. The second part is we're going to look at the symbols for electrons and positrons. Now, electrons, there are these E's over here. We give them a mass number of 0 because they have no protons and no neutrons, so they have no mass number. And what we're going to count is this -1 for the atomic number. An electron's kind of the opposite of a proton. So when a proton is going to be a 1, then the electron is going to be a -1. Now, a positron is something we haven't talked about before. A positron is basically like a positive version of an electron. So it's an electron, but it has a positive charge. And so its nuclear symbol looks almost the same as that of an electron, but it's going to have a +1 down below. In some ways, it's acting like a proton with just no mass number. So it's an anti-electron for a positron. So the first one we're going to look at is what we call beta decay. And this is the conversion of a neutron. So our neutron is our 10N to a proton, 11P. And so this happens when the nucleus ejects an electron, 0 - 1E. The neutron turns into a proton and an electron. So we're basically taking that neutron, we're converting that into a proton and an electron. So this happens in our carbon-14, which is neutron rich. It's got extra neutrons than what it needs to. And so what it can do is it can convert one of those neutrons into a proton, and nitrogen-7 or nitrogen-14 has 1 fewer neutron, 1 more proton, and is now stable. So a beta particle is the ejection of an electron. So a beta particle really stands for an electron. And we can see these kind of be used interchangeably. So when we want to express that concept, right, let's look at this carbon-14 to nitrogen-14. We can write a nuclear equation like this. So a nuclear equation is going to explain each of those isotopes that's involved in that nuclear process. Both of them are going to include their mass number and their atomic number. And what we have for this is whatever we start with is called the parent isotope. And whatever gets produced is going to be the daughter. And then the second part is going to be our radioactive particle that was involved in that process. So in this case, we can see that this is our carbon going to our nitrogen and ejecting an electron. So the important part is that when you balance a nuclear equation, the subscripts and the superscripts on the left side of the arrow must equal to that of the right. So it's not about your number of atoms anymore, or your atomic symbols. For nuclear equations, we're about conserving the mass number and we're about conserving the atomic number. So the things that need to stay the same is that we need to sum up our protons and our neutrons. That has to be the same for our products and our reactants. The other one is that the nuclear charge has to be consistent. So if we look at this left-hand side of this top equation, their mass number is 235 plus 1. And our right-hand side is going to be 138 plus 96 plus 2 neutrons, so 2 times 1. And you can see that both of those add up to 236. Down below, we're going to be looking at just their atomic numbers. So their atomic numbers, we would have, this should be 95 plus 0. And this is 55 plus 37 plus 2 times 0. I'm sorry, it's not that this one should be 92. It's that this one should be 92. That's what my mistake was. There we go. That makes more sense. And so that's how we can get both of these to add up to 236 on this side. And these should both add up to 92 and we'll balance. If that had been 95, we wouldn't have been uranium. We would have been americium. Right. So that was my mistake there. So it should be 92. Right. So let's practice that. Right now, we are taking lead, and lead's going through a beta particle emission. And so what we want to do is we want to figure out what this missing piece is, what our daughter isotope should be. So if we look at this, we have 214 on one side. And so we know that on the other side, it should be 214 minus 0. And so we have a mass number of 214. Our charge should be 82 minus the negative 1. So we should get 83. And then if we look on our periodic table, 83 corresponds with bismuth. And so our daughter isotope should be 214, 83 bismuth. And if we go through, we can see that that's exactly what we should be using for our balanced nuclear reaction. Another type of emission is what we call a positron emission. And so we eject a positron from the nucleus, and this happens when we convert a proton into a neutron. So that proton turns into a neutron, and so we eject out that positive charge in the form of a positron. We see this in potassium-40 in its decay process as it turns into argon. And you can kind of see how our mass numbers stay the same, balanced at 40, but we do have to account for that change in our number of protons. Electron capture on the other side is when a low energy electron enters the nucleus from outside the nucleus. So we kind of take an electron that falls into that nucleus and we take a proton and we convert it into a neutron. So like electron capture sounds like, then we should be adding in an electron to our nucleus. So when we look at that nuclear equation, you can see that this electron is a reactant because we're capturing it. And then we're going to be producing our new daughter isotope on the other side. So let's do some practice with that. And the first one is let's take this fluorine 17 and we're going to have it undergo a positron emission. So we know that we're starting with the parent isotope of 17,9 fluorine. And then we're saying that it's going through a positron emission. A positron is 0 plus 1 in an E. And since it's an emission, then we must be ejecting that. So we'll put that on our product side. And now we need to figure out our missing daughter isotope. So our mass number should be 17 to keep that balanced. And since both of them need to add up to 9, then it should be 8. And so if we look at what element has an atomic number of 8, then it's going to be oxygen. And so our nuclear equation is just like what we just figured out. The very last type of particle that we're going to talk about for our decay is going to be an alpha decay. Now, an alpha decay, this should be, is a helium nucleus. And so this happens when our larger isotopes go through a decay process, and they can eject this helium nucleus. It's got 4 mass number and 2 protons. So it's really 2 protons and 2 neutrons getting ejected together. So uranium goes through an alpha decay when it turns into thorium. You can see that as it decays down, it loses a large amount of mass number, and it's got to step down its number of protons as well as it moves its way into thorium. And so this is an alpha particle emission. So we had 4 types of decay that we talked about right now. We talked about beta decay, where we decrease the number of neutrons by 1, and we increase our number of protons by 1. And so these are examples of beta decay. We had positron decay, where we release a positron instead of an electron. And so our neutrons should increase by 1, and our protons should decrease by 1. So you can kind of see these are sample reactions here, and then this is the change that we're seeing inside of that nucleus. Because 1 neutron is a proton plus an electron. A proton is the same as a neutron plus a positron. And so this is kind of like the net change, even though these are the reactions over on the left. Electron capture is when we have those electrons or those beta particles on the left-hand side. And so we should be increasing the number of neutrons by 1 and decreasing the number of protons by 1. And then we have our alpha decay down here at the bottom. You don't have to worry about the spontaneous fission part. It's just an example of a type of reaction that we will see. We should be able to balance those reactions. This one in this case is just the californium getting split into 2 daughter isotopes and 2 neutrons. Right? But we're going to talk about that in the next lecture when we talk about kind of the applications of nuclear chemistry. So for our 4 types of decay, we can kind of sum it up in this process. You can see that both positron and emission and electron capture, they get us to the same place of where our daughter is going to look like. Our beta emission is the only time when our atomic number count can go up. And our alpha decay is where we can see the largest change in our atomic number. And so it's important to have a concept about how these pieces work together. So that way, if I wanted to tell you that you went through a positron emission, you would be able to correctly predict your change. Or if I give you a daughter isotope and a parent isotope, you could anticipate what kind of particle either needed to be emitted or absorbed in order to make that change happen. This is also a summary slide of the names of the particles and then the nuclear symbol. So that way you can also practice with those. So remember that when we balance nuclear reactions, it's not about balancing the number of electrons or neutrons. It's really about balancing your nuclear charge and your mass number, or really the number of protons and the mass number. Now for radioactive or for nuclear chemistry, we can go through what we call a radioactive decay series. So radioactive decay series is kind of a process that an isotope can go through as it works its way to get into that band of stability, to kind of come back to being a stable isotope, or at least a more stable isotope. And so uranium goes through this process here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 steps. You don't have to memorize these, but if I were to give you a series of decays, we should be able to correctly predict what the daughter is afterwards. So if we went from uranium and we said that it went through a alpha emission, we should be able to say, well, our uranium started off as 238.92. It went through an alpha emission, so it let go of an alpha particle. So we should have ended up at 234.90 for thorium. And then let's say that it goes through 2 beta emissions. Well, we know that a beta emission is the same thing as an electron. And so we should stay at 234, but we should have gone up, which becomes palladium. And then we can go through another beta emission. And we're back to our uranium. Right? And so we just want to make sure that we can talk about those processes like that. If we were to show you the daughter isotopes, we should be able to identify the decay process it went through. The other part that is talked about but doesn't involve a particle for our radioactive decay is gamma radiation. Now, gamma radiation is an energy and it's not a particle. And so we denote it with this kind of squiggly sign there. What this is doing is this is balancing out our energies as things go through a decay process. So gamma radiation is very high energy and it gets released as you go through these decays. Now, balancing nuclear equations is kind of like the main goal for today's lecture. And so you want to go through and you want to practice these. The solutions are on the next 2 slides. And so you want to make sure that you can identify what products or particles were released in order to make this process occur. So you can go through and you can practice those. So not all of the radiation is equal in terms of its decay. And so this diagram is kind of showing us the different strengths of radiation in terms of how well they penetrate. And so different types of radiation penetrate in different ways. So this is our alpha particles. This is our beta particles. And the last one is going to be our gamma. So you can see that alpha particles are really stopped quite easily. They can be stopped by skin or even paper. Right? Our beta particles proceed a little bit more than that. They need to be stopped by some type of metal. Some cases that can be aluminum. And then our gamma particles, they have the strongest penetration ability, and they must be stopped by a more dense metal, such as lead. So when we're looking at decay processes and we're talking about radiation, then there's different kinds. And that's why sometimes our alpha particle emitters, so radioactive materials that release only alpha particles, are not as dangerous or hazardous as something that's releasing those gamma rays, because their radiation can be easier to stop or more easy to stop. So for something like uranium, if it's only releasing alpha particles, if you put it in your pocket, then you're not going to feel any exposure because your genes are going to, or I guess the rest of your pant material would be able to shield your body from those particles. But if it's releasing beta decays because it's going through beta emissions, then that wouldn't be enough protection, and then we would have to wear something else. In the same way that when you go to the doctor's office and they take x-rays, they make you wear the lead vest. That's because the lead is a dense enough material that it can't be penetrated by those gamma rays or those x-rays. So let's look at these. This is another type of our nuclear reaction or a nuclear equation. And so this is bismuth 209 and is going through an alpha decay. And so we want to try to choose the correct daughter nuclide that should be produced. So if we balance our nuclear charge, we know that it has to be a 205 for our daughter. So that could be this bismuth or this thallium. We know that our atomic number needs to be 81 to keep that balance. So both of those still stay true. And so now what we need to check is we need to see which one of these actually has 81 protons. So if we look at our periodic table, 81 is definitely not bismuth. Bismuth is 83. So this should be our answer. It should be our thallium. Very good. This is another practice problem here, where we're going to write through the radioactive decay for our radium-224. So go ahead and practice that one. Once we have that, there's some more practice ones that we can do with our nuclear decays. So we can look at berkelium-249 or oxygen-15. And this is what we want to make sure that we can accomplish. So we should understand our different nuclear equations, and we should know how to write those equations. And so that's what we want to be practicing. Next lecture, we'll go into the chemistry of nuclear reactors, as well as the applications that we see with them, as well as looking at half-life reactions as well.